Cool. So what are we building here? The context is obviously Kafka. Redpanda is the name of the product. It's also a really cute pet and mascot. We're building a real-time engine for modern applications where Kafka API compatibility is only part of the story. Fundamentally, we wanted to eliminate Zookeeper and make it easy to run. So abstractly speaking, we were thinking about just having a single binary that you can just ship around and SCP to a bunch of computers. We'll talk at length about specifically zero data loss using Raft. So instead of having like your log flush rate to disk be like 1 on the Kafka broker setting, you can choose it dynamically with like X -1. It actually means that there was a full quorum write and data was flushed to disk. We rewrote it from the ground up for modern hardware. You'll see what this means and like what is actually 10x faster. It's basically P99K latency is what we claim. So talk about foundations and set the context. I speak relatively quickly. If people have questions, let me know. I can also slow down. And I've had 2 cups of coffee, so I'm seeing the future. Fundamentally, this graph is really just a graph of what has changed in bottlenecks. You guys know this. For context of others in the room, this is my view of streaming innovations as I've been part of this for the last decade or so. RabbitMQ, really big innovation, and I'll give more context because I've been talking to a lot of business people about this. Really like shatter massive products in the enterprise. It was really permissively licensed and people loved the API. I think it was AMPQ. And it's just like sort of the abstraction. It didn't necessarily scale for, well, full stop. Then Kafka's, was my view on Kafka's innovation was that it was trying to take advantage of basically cheap spinning disks. Were you guys, but I know preaching to the choir. Pulsar innovation later on was really to disaggregate the compute and the storage. And the context for Pulsar is probably some Pulsar devs in the room too. Was Yahoo, right? And so Yahoo had this massive HDFS clusters. And they're like, oh, Amazon and Google are doing this thing, like specialized in hardware. If we decouple them, we can basically lower the cost of doing streaming for them. Kind of what happened at the same time is S3 became the data lake, and it became the disaggregation of compute and store. Hence, the Snowflake launching the most successful public offering in the world. But really, kind of what matters here, the point that I wanted to drive at is performance of CPU by the numbers. So let's look at them. CPU frequency is now 3 times faster than it was a decade ago. So actually not any real gains. Computers have gotten about 20x more cores. So this is actually where the substantial improvements have come from. These are it says 100, but it's actually 1,000 times, like a modern NVMe is about 1,000 times faster than a spinning disk was over a decade ago. And they're cheaper. So if we go here on like the 2008, you can go to Black Blaze, which is a company that hosts and provided that storage. They have all of these numbers over the last decade, and it shows like the cost of terabyte per SSD was roughly $2,500 a decade ago, and it's now about $200 per terabyte that you can rent this on Amazon. And if you were doing, I guess a lot of folks here are very sophisticated and mature, so maybe preaching to the choir, but when we were doing cloud 10 years ago, you rented maybe 1 gigabit per second NICs on Amazon. You were doing 4 cores, like that was the cloud over 10 years ago. And now you can rent 100 gigabits per second NICs on Amazon and actually get the throughput deliver on the i3, new i3, probably from the 8x large instances and above, right? So i3 EN Metals, i3 8x large, 16 large, and like just the whole machine. Which to me, as a user from cloud and seeing, a decade ago when I was building an ad tech in New York, like a gigabit per second was actually optimistic. So more stuff about, I have about 30 slides, so I'm gonna time myself. I'm gonna go through a lot of the content relatively quickly, so to get to the interesting thing, which is the new fundamental architecture. So why does computer actually feel faster? It fundamentally this came from like IP instruction level parallelism. So, and you can think of it like RPCs, right? So a CPU is actually a network of ports, and you can make an RPC from the front end to the executing machine for like floating point arithmetic. There's a couples for additions and so on. And the next big improvement here is, of course, instruction prefetching, branch prediction, right? So like hints at the compiler, and it studies the stable workflows execution, and then it says like, you're probably likely going to take this path. So I'm gonna just like start executing these things. We now have deeper cache hierarchies. So you have like your instruction caches, your data caches, and then like, of course, all the way up to main memory and then NVMe. And even with the new 3D crosspoint technology from Intel, the chalcogenide technology, which takes, I think, about 1 microsecond to invert the charge on the actual chalcogenide metal on the 3D crosspoint hardware. So just like massive data caches fundamentally. So the trade-off here, and kind of like why computers feel faster, is that you get this massive performance improvement for predictable workloads with really fundamentally this instruction level parallelism and all of the technologies that CPUs have put in practice. At the trade-off that if you miss, then like you have to invalidate your entire pipeline, and that takes longer. So just kind of setting up the context. So in storage engines, really, and I hope to focus the rest of the conversation on us and the storage engine, and actually try to get us low level. I'm just trying to get to the place where we can have a discussion. Is compile time really helps us a lot in thinking in terms of profiling, just basically telling the linker to eliminate a bunch of that code. Helping the branch predictor, pessimize actually different code paths. So this is super useful in, let's see, checksumming, compression. So where you have like your LC4 64 kilobyte chunk encoder for like the Kafka chunk encoder, you can just always pessimize everything else, because for us, this is we are a storage, we're a new storage engine, and the only interface is the Kafka batch model. So it's in like, that's literally the disk interface, and everything has been optimized around it, including like rewriting parts of the compressors to say like, for LZ4 is this, for the Z standard, it's always very likely that you're going to have multiple chunks. Well, gzip sucks as it's actually very CPU intensive. It's good for compression, but very, very CPU intensive. It's like an order of magnitude larger than the others. And snappy. So that's one. A second one that was really helpful for us in terms of trying to improve the Achilles heel was LTO. So we try also PGO, which is profile guided optimizations, where you take a binary, you tell it to record a trace to disk, and you say like, this is the typical workload, record a trace to disk, and then rerun the linker again and say like, optimize this. That was exceedingly slow, and it pessimized everything else. And so we didn't feel that PGO was useful, but we did find LTO being super useful. So the parts where LTO are useful, in particular in a C++ code base, is eliminating final class inheritance. So let's say that you have a classical inheritance, right? Like you have, for example, your allocator, you have like an abstract allocation interface, and then you want to hide the details on that. It's really slow for us to link. It really takes a long time, like multiple seconds to do this. But it gives us about 5 to 7 performance improvement. The bad part about optimizing for instruction caches is really difficult to debug. And when you get a stack trace, you basically get like 0x, go fuck yourself. Like try to reverse a back trace to actually something meaningful is really difficult. And it is actually becomes even more difficult in a thread per core architecture we will talk about in just a second. Other things that have significant impact for us is because we have exactly one case which we're trying to optimize, which is we're trying to shove bytes from the NIC, with checks dominance on, to disk as fast as possible. We understand which functions must be inline to give us like the right throughput that we're expecting. So being able to tell the compiler and force the compiler to inline particular one-liners are super useful. And then the other one from an instruction cache level is using sophisticated data structures. So I think Jeff Dean participated in the Absol flat hash map 2 cache line validation story, where so it uses 16 bytes as the cache line, and it stores basically a bit vector. And so to find an element, I think they guarantee some amortized cost of two cache lines. All of this have helped tremendously. And this also just adds more color, as like we weren't, of course, the only ones to understand that CPU is the new bottleneck, and the NVMe SSD devices are now super fast. And so like things have simply moved around. You can't eliminate things, you're just sort of moving things around. Great, so let's talk about low-level architecture. First of all, questions there on CPU is the new bottleneck. I'm just setting up the context, probably nothing that most people here will probably agree with that.
Do you spend any time optimizing TLS?
I assume you're not saying thread local storage, you're saying TLS, the handshake, the
security SSL.
Not yet. So what we do is we eliminate at compile time, we do one thing only, which is so we eliminate all of the old code. We say like support TLS 1.3, like eliminate all of the older code, and then we compile, sadly, for Westmere CPU architectures, and that's just like what we have to compile to so people can run it on Amazon. But if this was, when we run our cloud, which will come probably in like February or so, that's as GA, we'll actually probably ship compiling infrastructure to these edge machines to optimize for that particular CPU architecture, like localhost CPU architecture. Really on things like bit vectors, so compaction. We use roaring bitmaps for compaction, and being able to XOR maps of like bit vectors using AVX2 instructions as opposed to just SSD3 instructions really have a big performance impact for us. But sadly, the only thing that we're doing for TLS as the security protocol is just targeting the Westmere architecture and say like, that's just a mid instruction set for this. It helps a little bit, but quite honestly, probably not significant in any way. Sean, did you have any other thoughts around that? Like what would you suggest would be like additional improvements?
I've never really investigated this, but I can tell you that our CPUs at LinkedIn spend a lot of time doing this.
Yeah. So what we, let's see, I'm trying to see what I can share from another company I worked at. What other companies do is that they offload a lot of this to FPGAs, and that was fairly successful. I think there are some expensive NICs that you can buy that will just like give you an unencrypted socket from the application level, and the FPGA will do the decryption close to line rate. But it is more expensive, and the NICs are expensive, and you're looking at 40 gigabits NICs. That's like really, I think, the best optimization I've seen. It's just offloaded entirely off of the stack.
Okay, thanks.
Cool. So 30 minutes left. Okay. I want to move faster now. So what is the observation here is that CPU is the new bottleneck, and so we should treat everything asynchronously. In particular, dispatching IOs via IO submit or with IO uring, which is Jen's Adobe from Facebook, his latest recent kernel patches. I think they landed in 5.6 and above. So those are useful, though actually in practice we found that the difference between the way we architected IO submit with libaio versus IO uring was only about 7 to 9%. There wasn't that massive improvement, and it happened to be this particular architecture that I'll talk about in a second. But that was the gist: is like treat everything like an asynchronous like you treat a network call, which means like, they may fail, you may need to retry, you need to have quotas and back pressure, and all of this other infrastructure that comes from making a network call. Okay. So we built on a framework called Seastar that I own. I think the two things that are useful here is that futures are like actors. So whoever has written code in Akka knows this. The minute you introduce Akka into a code base, the whole thing becomes an actor. It's like you just have to wrap things into actors because it's easy to do, and it kind of like lends itself nicely. I have never written Orleans on the Akka. And so Seastar futures are very much the same. They are a viral primitive. What's nice is similar to actors, right? You can like mix them, reduce them, filter them, change them, complete them, generate and fulfill them, slip them, require them, expire them, etc. There's all of these useful primitives. And what you do when you have this viral and very opinionated, by the way, there's no other way to do to write code with Seastar. Like you simply have one primitive, and those of us that have written code for, let's say like Facebook, Wangle, and the other C++ frameworks out there, because we built Concord on top of these other frameworks, where you have multiple concurrency paradigms inside a single framework, is really difficult to understand as a programmer when you're writing code. What is the actual useful thing? Like, what is the right paradigm? Versus when you have one and it's opinionated, some tasks might feel a little bit kludgy, but it actually is good because it forces asynchronicity in your thinking. And fundamentally, I think what it changed is that it forces concurrent structure, where simultaneity, right? So parallelism is a free variable. You can write the code in futures and execute it inside a single CPU, where you're telling the compiler to co-await and say like, suspend this frame and then execute this other frame, or you're telling the runtime to execute these two things in two separate cores, but it forces you to write and focus on the concurrent structure, right? So a correct concurrent structure from the get-go, and only one way to do things. In Seastar, so this is how it looks before I dive into this. Sometimes it's not pretty. This is how it looks in C++. This is our wrapped implementation. And so a couple of things to point out here, and then I want to talk deeply about thread per core, is when I talked about treating everything like a network call, I mean it. So get a scheduling group, for example, is the same. It uses a similar algorithm as the Linux kernel completely fair scheduler. So it's basically a hierarchy of shares, and you can create more groups in this hierarchy of shares. But it says run this lambda with this particular share hierarchy, and it's just an integer, so it's relatively cheap. It's an integer ID to a thread local, TLS in the thread local sense, thread local storage. But this other one that is perhaps more interested is that from this core, we're making a message pass to this remote core called shard. But then even when we do that, we're telling it, by the way, use this service group. So this is where back pressure starts to kick in, right? So it's fundamental from the ground up. It's not just a back pressure at the TCP level where you're just deserializing a TCP buffer and parsing the Kafka batch header, etc. You're actually saying to make a call to a remote node, and it could be a remote socket. So let's take the case of a two NUMA domains where you have two CPU sockets on two separate NUMA domains. In order to make an RPC call, an IPC call, inter-process call to a remote core, you're telling the scheduler subtract one share from this scheduling group and this service group. And so it's really from the grounds up this approach of back pressure. The way this works is Seastar, we use this framework called Seastar. It uses a thread per core architecture with locked memory. And to give you even kind of a deeper sense, there's a body allocator and we have to work around this. Sometimes it's really painful. Is when you start up the computer, it allocates one segment, right? So classical body allocator algorithm here. And so let's say that you have, for simplicity, 10 gigabytes of memory. There's 10 cores. Every core is going to allocate the first body, which is a gigabyte, and that memory is going to be locked. And so typically what happens for production systems is you reserve, like maybe a gigabyte for like cron or other things that are going to use, your DNS and whatever. And then you lock the memory. And so what that does is that if you make, so there's two things. One, the allocations are core local. And you have to be very careful about how you share memory between threads, right? Because it might be accessed from a totally different NUMA domain. So and the way Seastar does this is that every core has an outgoing mailbox for every other core. And so there's a loop, it's called the reactor loop. And this is, those of us that have written financial systems, there's nothing novel here. HFD has been doing this for like over 20 years. So there's a loop on every core, and the loop will poll first for IO, right? And so you get 500 microseconds to execute a loop. And if you fall below that, above that 500 microseconds, Seastar will actually print a struct trace and says this function took longer than 500 microseconds. Why is that useful? The reason that's useful is because there's a single loop that is polling and is doing everything, right? And the point here, the reason why that works is that you wrapped every single computation in a future, and future are cooperative units of work. Every time you return a future, the Seastar scheduler can yield different ordering, and it has priority where IO ripping from the NIC has much higher priority than executing CPU intensive applications. The reason this works for IO heavy engines like a storage engine, and this wouldn't work well for like if you're trying to do like GPU computations or something, is that we are explicitly choosing to prioritize IO over a lot of the CPU intensive tasks. And so why is that? It's mostly because IO, if you treat it like any synchronous network events, you can just poll the kernel with, I think after 4.19, Avi submitted a patch to kernel where it added like the ability from libaio to just poll events. And so you submit a network call to the kernel, and then every IO you say like, what did you complete, right? And so it makes sense to prioritize the IO. And since every core is doing this, you can only block for some amount of time. Like fundamentally, if you need to decrypt the request, or if you need to decompress a buffer, like there's no yielding, right? Like your CPU intensive for some particular task. But you need to figure out a way to yield work so that you don't propagate latency to the user interface. Very classic. So it uses a network of single producer, single consumer queues. There's often two patterns in. Ooh, time check. I'm really going long here. I want to skip a bunch of slides, but this is like a foundation.
I have a question. How do you maintain this locality when you get to do file system operations?
Oh, great question.
You don't own the file system from a core, right?
That's correct. So there's two things. One, you can tell the Linux kernel to allow the core that submits the IO to be the core that reaps the events. There's the Linux kernel setting. And two, you can coalesce the interrupts. There's another Linux kernel. And so, and then you spread the interrupts around, right? So those are really the only two techniques that you have from the Linux kernel level. So it remains stored local. I mean, once you cross the barrier into like direct AIO, when you're flashing to XFS or something, like you don't control that, right? This is only for like within the applications, and you can tune the kernel for some particular settings. The other setting that is useful is to tell the Linux kernel to not merge your block IO. Right? So what happens is when you submit a bunch of stuff to, might be the next slide. Well, this is the impact. You can tell me that. You can look up Seastar.io, but I wanna, this is useful in this discussion. So right, so you can tell, oh, the other one is disabling IO merges. And what it means is that in this picture, let's say you have whatever, some memory aligned buffers, and you can ask the file system what the memory alignment is. You don't want the Linux kernel to think like, oh, I actually know better than you. let me group this into a bigger thing and let me do a bunch of reallocations. So a big part of getting performance is to disable set the Linux scheduler for no-op on the block device level. And I think those are the three things. So it is interrupt coalescing so that you can rip them in batches. It is distributing the interrupts so that the core that dispatches them can rip them, as opposed to dispatching core 0. And the reason core 0 is the thing that matters, is the default for a lot of, everyone has seen basically the picture of a Linux scheduler where like core 0 is doing all the work and there's a bunch of construction workers sitting around. It's because it's the only core that is guaranteed to exist. And so anyway, so when your program starts, you can tell it like reap all the benefits. And those are, I think, the main three things that have yielded particularly good tail latency improvements for our storage subsystem. Let me go back to this one case. You guys can go to Seastar.io. So I didn't want to add a bunch of our benchmarks also because I only had 30 minutes to put together this presentation. But roughly you can see sort of an order of magnitude improvement in general. For this is, I guess, just for memory and CPU bound requests. Also, there was a new paper on NSDI 21 or 20 on the impact of thread per core on tail latencies. So let's talk about high-level architecture, because this is maybe more generally useful to the rest of the audience. Shoot, I only have 18 minutes left. We'll probably get through half of this, and maybe we do a comeback here. So on ring 0 is so we're a RAF-based system, and which means and the reason we wanted this is of course we didn't want to have a dependency on Zookeeper. It was part of the core product value, and so we rewrote it from scratch. And then we went. Dennis, we were very lucky to have him. He joined the team. Super psyched on working on actually extending Jepsen, and we maybe should talk about that at some point, where like evaluating the histories of Jepsen in the classical sense without adding a little bit more metadata is n factorial in computational time. And so we applied a couple of other optimizations brought in from the Cosmos DB team to allow for linear histories, and so we can test the system for longer. So, but at an architectural level, when you start up the system, you have three like Redpanda binaries, and you set the configuration. That is your degenerative case. And so anything else sort of bootstrap from this ring 0. This is similar to the Kafka controller. You know, in Kafka, you have a controller. So there's ring 0, elixir leader, just classical leader election to Raft. It is stable leadership, which is nice particularly for throughput. And actually, I take it back. Yeah, for throughput. And then every other group is and so the leader of ring 0 becomes the cluster controller, and then it does the physical partition allocation of like which physical compute is going to own that, and every partition is a wrap group. And what we did there is that we actually then optimize. It became a mechanical translation. We didn't want to invent a new protocol. What we wanted to do is like, we're good at making things fast, the team. And so let's start with a known protocol and actually focus the engineering work on making these things fast and scalable. And last time I tested was about 360 something thousand groups per computer, and we're probably going to remove that limit at some point, given enough oversubscription on a machine of partitions. You're running into network bottlenecks. But anyways, so this is the high level architecture. Lucas, were you going to ask a question?
Yes. Did you implement your own ref library, or did you use any like existing library?
No, we implemented our own from Seastar. So if you go back here, this is literally how it looks. It is asynchronous. Let me see, with the annotations in particular, it's useful. Because futures are a viral primitive, there's no way. So threading is a fundamental building block. It's almost like a mental decision of how you're going to build your framework. And there doesn't exist a library that understood a thread local approach with futures as a yielding mechanism. That was in C++ that we could use. So as far as I understand, there's our Raft implementations, which we're going to open source all of this next week. So we want you guys there, if there is interest in exploring something together, we'd love to figure it out. And I know Scylla is also trying to write their own. I also know that Ceph, the file system at Red Hat, is looking at their own consensus protocol. But when I started this in 2019, there was nothing. So we had to rewrite it from scratch. And the reason was we wanted to propagate tail latencies like from the lowest level. It was like it was a conscious decision, and it took us 18 months. So maybe from a company building perspective, we should have used an open source library, but we wrote it from scratch.
Thank you.
Sure. Okay, so this is probably the most familiar picture for, maybe not, but for those of you that have been working in, I want to leave 5 minutes for questions, just so everyone knows. Let's see, right, so you have a fetch request, sorry, a produce request rather. The fetch request is much more complicated because of consumer groups and so on. So I want to talk about produce requests because it's maybe the simplest one. Through the layers of kind of how we went about re-architecting this thing from scratch, where Kafka, and I talked about in the beginning about optimizing for structure and caches, like how this, where's all of these pictures come together. And so if you look at this architecture, like what does this really mean in practice from when, like in code and how it executes. So you have a Kafka request at the top, maybe a cloud of Kafka requests. They come in through an RPC handler. I'll tell you how we guarantee compatibility. But then fundamentally, there is no global metadata cache, right? Like if you, I'm not sure off the top of my head, what's the last time I looked at the Kafka code, but you have to look up, one, are you the owner for this partition? And like the machine, you know, did I get the right machine, or do I have to tell the client, like, I'm not the owner of this partition, or this partition was deleted, or like, you know, all of that. So you do this metadata cache. Instead of it being a global data structure that people share around, even if it's read-only and you can guarantee, well, with Kafka is eventual consistency of the metadata gets propagated to all of the nodes. So even with relaxed consistency guarantees, is a totally different approach, because what you're optimizing here is for latency. So you do consume additional memory on every core to keep a particular view. You don't keep the whole thing, because like there's a computer global allocator, so we don't have to get into that. But fundamentally, this is maybe the most interesting part, where every core holds a view of what partitions this particular machine holds. And so everything else is not materialized. And so when a request comes in, so we can make a request locally without changing context, whether this request is valid. That's a huge one. And then similarly, which one is the partition owner? So which core? So at the lowest level, being a thread per core, we actually guarantee single writer, single reader for a particular file handle, right? So, you know, at the end of the day, you have segments, and that's what a partition is. And segments get rolled, and our default is a gigabyte per segment. But there's a single core that owns the reads and writes for that particular partition. And so the partition router looks up and says, hey, actually, core 1 happens to be the RAF leader in this particular case for this request. I'm going to send via SPSC, via a network of SPSC queues, a request to core 1 to then do two things. One, dispatch it concurrently to the followers. Sorry. Well, concurrently on the core in parallel in the network execution. And also dispatch another network request to storage, which is, again, if you treat everything like a network with backup, retries, failure domains, guarantees, etc., and back pressure in particular, this is sort of a really useful thing. And then when you finish the acknowledgement, you don't just return back to the handler, because that would violate basically memory ordering and guarantees. So you push back a response to the network of SPSC queues. And those are small messages. So let me give you orders of magnitude so that you can understand the impact. Every core could probably handle, I don't know, tens of millions of futures, because they're relatively small structures. I don't know, say 16 bytes probably, maybe a little smaller. So I need to look up the size of the struct later. But anyways, you can have millions of them. And so you send back an RPC request via like an RPC like the mental model. So just a memory order right to the SPSC queue. And then in the next loop, core 0, which is the RPC handler, will reap the events on its incoming queue, and then we'll respond back to the handler. And at the same time, right, like the other RAF instances have been doing a similar request. So, oh, I should have just done this picture. Okay, well, I just explained all of this. Guys, stop me if you have any questions. We have 4 more minutes. I want to cover.
You have, okay, so if I have a Kafka client, I'm not establishing a socket per core. I'm establishing a socket per machine. I happen to land on some core which may or may not own the partitions that I care about.
Correct.
And that core routes my IO through the entire machine.
Let's be more detailed when you say IO. So it doesn't, there's no.
Consume requests.
Yeah, so it routes metadata to the correct core, but it doesn't like and then so you can have, that's a great question. You can have read-only memory from other cores, but you can never mutate memory from other cores. There's like this explicit protocol for handing off memory to another core.
Do you eventually move my socket over? Is there any notion of stickiness? Like if I'm a producer for a particular set of partitions and I happen to land on the worst possible core, like wrong domain, wrong everything.
Yeah.
Am I
That's a great question. That has to be an extension to the Kafka protocol. The way we do it internally is we actually just retry reconnecting. Two reasons why.
Do you need to extend the Kafka protocol, or can you pass over the socket to a different selector, a different event loop?
Well, no, it has to be a different. We want to offer it we want to rip it from a different event loop, because remember that in order to get good locality, and this is like it's not every thread per core architecture has this problem. We'll solve it. Basically, you don't know if that TCP connection is actually going to be steadily producing data to core 0, or steadily producing data to core 1, or it happens to produce data across a bunch of multiple cores. So it's actually a much more difficult problem than just moving the socket on a stable write. For stable writes, what we do on our proxy.
That's true, not per write, but you can learn over a period of time.
Yeah, it's true. It's hard. We haven't done it. And so if you look at the Linux scheduler assignment, when you hash the 5 tuple on the TCP connection, right, which is like the external port, the internal port, the destination address, and so on, like the Linux scheduler with the default network allocation will just land it on a particular core. And every core reaps particular events. So once a core opens the file handle, it'll own it forever, right? Like once that particular core accepts the connection, it'll own it permanently. So to get around some of this internally, remember, this is only external on the RPC. So externally, to be on our own HTTP proxy, we actually try to dial multiple times to the machines until we get a good port assignment. It's hacky. This is what we have today, but it works. And then internally on the internal TCP connection, right? So on the middle thing here, we actually open some small number of TCP connections. So let's say every computer opens up like 3 TCP connections to computers that happen to be in that particular quorum. And that'll give us some form of locality, because you actually have the same problem when you're sending data, let's say a heartbeat, but you only have 3. So you have 144 cores, but you have heartbeats to that destination node coming from multiple nodes. And so we lower the cost of the SPSE network by opening up multiple TCP connections. It works well in practice, but there's definitely improvements there. I think for smaller clusters, you actually can have an n² number of connections open in the cluster, and it would be fine. So let's say 10 nodes or something, and there would be no movement. But right now we do, I think, a default of 3. I have 5 minutes. I'm probably going to stop the presentation. And then we didn't get a chance of reviewing draft versus the ISR protocol and synchronicity, etc. Randai, do you have more questions?
Actually, I had a question.
Go ahead.
So hi, I'm Owner. So
Owner.
It looks like, if I'm understanding it correctly, you're pinning a partition to a core.
Yeah.
The ownership of a partition to a core.
Yeah.
So like a produce request could have multiple partitions.
Yeah.
So do you do like some sort of like scatter gather type of thing?
Exactly.
Okay.
Yeah. And kind of I really skipped through this, but because we're using DMA, we force people to use XFS because XFS is also first excellent. But it has one particular feature we care about, which is sparse file system support. It means you can dispatch concurrent IO to that. I think ext4 also supports this, but I know XFS. So you can dispatch concurrently to, let's say, the number of queues that the NVMe SSD controller has. And this is really helpful when you have like a super hot workload that, let's say, replication across data centers or something. You can just dispatch, we could basically drive all of the devices to their theoretical limit in terms of throughput. And then latency will build up at some point. If you're like producing higher than the throughput, then like you build up latency on the disk. So typically an IO submit will take like 100 microseconds or so, probably maybe 130 microseconds, and then at some point the disk gets overloaded, and then because like from the ground up is built using this back pressure mechanism from the scheduler, it'll eventually propagate to a core, which eventually will propagate to the Kafka client, right? So if you're using AX1, it means like the client will not send their next request until it receives an acknowledgement from the previous thing. And so really bottleneck, we can observe latency bubbles straight from the NVMe device and then propagate that correctly, even across cores through the network. We have 2 minutes left. I don't think I can cover more slides. I went through it super fast. Hopefully this was useful for people. And stop sharing, and then I can just see people and ask questions. I don't know if.
So a quick question. So if some company they're already running Kafka and they want to adopt your product, is it true that they need to shut down the whole Kafka cluster and then run a brand new? So there is no like smooth transition in between.
And this is by design. We didn't want to speak inter-broker communication. Like I talked about this on the data engineering podcast, but basically if you look at the number of versions per, let's take the produce and consume requests, so fetch and produce. There's basically like 12 versions with the new flexible protocol and multiple like Kafka client versions and multiple broker versions. So in totality, there is something like 144 APIs just for client side requests. And so it's too much. And so we said, we'll speak the client protocol because you have enterprise applications that want to leverage this. But internally, we want it to be totally different, and we want it to be, that's the only guarantee we wanted to give. So currently our on-disk format is actually quite similar, but we hope to change a lot of that. Like our offset index is different, our time index is different. We wanted the ability to innovate, and you kind of have to pick your battles. And so we're like, well, we'll do this, and then people can use Mirror Maker to push data over.
I have a question about cluster balance. So one of the things about Kafka is that it doesn't shuffle around partitions or topics. So
right,
if you have a cluster and you add a broker, no one cares, nothing happens.
Yeah.
Does this behave any better? Because you're saying that you still have segments for partitions.
Yeah.
And the Kafka protocol actually never mentions segments. They're not a part of the Kafka API ever.
Yeah.
Do you suffer the same balance problems and needs that Kafka does?
So there's saturation not just on disk, but also on CPU and network. Actually, when you start to drive taller and taller computers, network saturation becomes more of a problem for a lot of people. And especially when you start to oversubscribe the machines. Let's say you assign 70,000 or 80,000 partitions per broker, and so that's actually much more difficult. And there's two solutions to that, right? Like one, you either proxy the writes, and Dennis is working on that. And then two, because we are a RAF-based system, we can I didn't talk about shadow indexing, which is the ability that we actually will read transparently from S3. That's probably partially implemented. And so what we have to transmit to the new machine is basically the segments that haven't been pushed to S3 stably yet. So you can push an index to a read replica, add it to the Kafka group, do a joint consensus transition to add the new broker, and actually the total
you
number
can
of bytes.
expand and shrink the ref group. I understand that. But the question is, do you do that automatically?
It's exposed through a curl API, but not yet. We plan to. We just don't know what's a good timeline yet. We need more experience with the product, to be quite honest. Like, do we check every 10 minutes? Do we check every 5 minutes? Do we check every time the node adds? I don't know what is the good timeline. Most of the time, people aren't at the scale that you guys are seeing. And so for them, adding computers is actually about partition capacity and less about resource saturation for the majority of Kafka users we talk to. So what we have done is instead of making it automatic, you just have to make a curl request and say like, make this transition. And that's basically, it's just exposed to an HTTP request. So the mechanics are there for movement. We just haven't, we haven't automated. I don't know yet what's the right, honestly, I just need more data. I need more people using the product at a larger scale. Did that answer your question?
Yes, and as you said, keeping Kafka in balance is a problem for us.
Yeah, it's hard. There's another use case, another like big tech company that we're working with, and you know, I think network saturation is also such a difficult thing. I don't have an easy answer. I think that.
What about SPI? So, for example, do you allow users of this product to plug in their own authorizers or other broker side, let's call them message interceptors of any form?
Oh, yeah, we do. We have a WASM engine. I didn't, I think we're at 3 minutes. I'm happy to stay over. I have another 20 minutes left, but if people need to drop, feel free. So we didn't talk about it because this talk was scheduled for an hour. We actually ship a WASM engine, and we wrote a protocol where you can subscribe WASM transformations. So the first one is going to be just JavaScript as the SDK. So you can think of like an observable in JavaScript, like subscribe from this topic, make a transformation. I think for those, it's not for high throughput or low latency use case, but actually for convenience or GDPR compliance. So we're talking to another huge food delivery company, and they use they're thinking about using the WASM engine to guarantee GDPR compliance for their machine learning workflows. So so you get a request, Kafka style, and then the engine will just submit basically an IPC request. It says like interpret this memory in JavaScript as a Kafka batch, and then create a callback and return a materialization of this message, and then save it to disk. And that's done asynchronously, right? So because everything is
horribly slow, right? Because Kafka compresses. If you intend to read payloads, you need to unzip them. That'll kill your CPUs.
Yeah, that's fine, right? Because for a lot of people, like I mentioned, I think that most workloads, if you ask a lot of Kafka users, they're like nowhere near the throughput of Kafka, that like the limit of Kafka. I think what they're looking for is really primitives to build applications, and it's not, I mean, it's up to them, right? So I think people can make a conscious choice of how to run it.
I have another question about your metadata. So you said that you keep some part of you keep the metadata relevant to a machine per core. Is that what you said earlier?
Yeah.
Do you run into memory issues? So modern machines, 64 physical cores, 128 virtual cores. 50 megabytes per copy of Kafka metadata, let's say.
Maybe. I think you're thinking of a stray representation of the upstream Java. We don't necessarily use the same representation internally. Okay. But even if we do that, so that's That's fine. Let's say 50 megabytes per core. And typically very tall computers will have like 768 gigabytes of memory. Like if you look at Amazon.
Those are a little extreme. Yes, you can buy them on Amazon, but it's an arm and a leg. Okay, so you're saying you don't keep the whole cluster metadata, it's only machine metadata, and you have a compact representation of that?
There is, I mean, you have to keep some global view, because otherwise you can't tell like hold on, I'm trying to remember the first protocol.
You have to answer fetch metadata requests, right?
Exactly. So we keep some metadata and we can always fetch it. But there's basically the idea here is that there's some metadata that is always materialized per core, which is the things that is most commonly used. And then there's some metadata that can be rehydrated, but it's all local. Like it's okay to make a remote core communication, let's say to core 0, to get the global cluster view and then return it to the client. As opposed to materializing the global cluster view for every core.
Yeah, because that's, at least in Java, expensive.
Yeah, and you can do a lot of bit packing in C++. It's relatively straightforward. But I mean, there's basically essential complexity. Like you can, like if you're trying to replicate data, like you have to send data. If you need to answer metadata requests on every node, then you need to answer metadata requests. It's like things that the protocol imposes on the implementation. We could do tricks to kind of try and solve it, but there aren't that many tricks.
I had a question about the internal message routing. So you said that there's a core, each pair of cores has a queue. Is that correct?
Each core has two SPSC, actually an n square number of queues. So it has one per every other core.
Per every other core.
Yeah, so if you have 16, you have 16 physical cores or virtual cores, every core will have like 16 SPSC queues. And the reason is it's basically cache line invalidation and atomics. You can say like, I'm gonna write this with like relaxed memory, and then I'm gonna read this with strong memory, and you can do that kind of trick relatively cheaply. That's what makes it kind of a network of SPSC queues. The alternative is you have a burner core. So Bobby Blumo's algorithm, right? I think his PhD was on work stealing. There's many ways to skin this cat. The way Seastar chose to skin this cat is really through a network of SPSC queues. So every core will have like 16 instances of an SPSC queue.
So if the receiving core, how does it choose among the incoming queues? What requests it will service?
Yeah, so it'll prioritize IO, like I mentioned, and then it'll just like pull it'll just round robin through the other queues until it sees a task and it'll execute. It's basically just like receiving mailboxes, and so it's just like, do I have a message in this mailbox? Do I have messages, and so on. And then it has another different priority for locally produced mailboxes. That's the highest priority. Once you run out of work, and there's a scheduling algorithm. There's basically a schedule on how it does this. I have to look up the reactor code, but I think Glober work on a similar schedule for the KVM. My hunch is that what he told me is that it's very similar to how they do a lot of the schedulings in the low level there. I need to look at the code to be able to answer like what is the actual schedule. But there is basically the TLDR is that there isn't a schedule. It prioritizes IO, then it prioritizes locally produced mailboxes, and then it'll go on and pull the queues. That's basically it.
Okay, thanks.
Hi, Kyle here. I'm curious. So, sharding the state of the broker amongst NUMA domains, that seems really intuitive to me. That would really help with throughput, and latency. But I'm curious if you have a sense of like the real impact it would make in the system if you like didn't shard to individual cores. Does that make sense? Because it seems to me like a lot more work to go that far than it does to just to shard the workload across, like, say, you know, the 4 or 8 NUMA domains you have on a system.
Yeah, I think to understand the intuition here is there's basically 2 cases. There's either a lot of work or there's no work. When there's very little work, when the system is not saturated, it's a lot more work to have this stuff and like a lot more memory and stuff. When the system is actually saturated, there's actually millisecond level pauses to go across the core. So this optimization is really for tail latencies, not necessarily. I think that's just mostly for tail latencies, and it does improve throughput, but you know, I think pick your battle. We have to pick our battle. So that's the intuition that we've seen in real life, is that when the system is at full tilt, then you see actually latency pauses, latency spikes. But other than that, if the system isn't, like, if you're running at some low level of utilization, it's probably overkill for that. The goal is, I feel like when you're building a system, you have like some primitives and some opinions of how you see this thing working, and then you try it and see if it works, because like you have to test it in real life. Some things work nicely, some don't. Like the network problem that Radai was pointing is a real one. That's something that we haven't fixed. It's definitely higher memory use in some scenarios. Actually, if you look at it at a machine, it's okay. I think actually most programs will probably waste 100 megabytes of memory. So the superficial ways that it seems like, it's like, oh, there's all this waste, is actually not that bad in practice. But the trade-off here for having this network of queues is that when the system is not really busy with user events, then it looks superficially busy, and you're like, I don't know what the hell this thing is doing. I'm only sending in 100 requests per second. Why is the CPU like 80% or something like that, right? Like, it's because it has to loop to understand, and then there's a scale down algorithm. Yeah, hopefully that answers your question.
I see. Yeah, thank you.
I have another question about migration. So we already said that online live migration of this thing, you basically have to shut down a Kafka cluster and start this in its stead.
Maybe, because what you do is you set up, probably you have 2 live clusters. I don't think there's any company
data. So this is where I'm going. Do you honor the Kafka internal topics, _ consumer offsets, etc.?
That's the question.
They are both an API and not an API. So my question is, okay, I can move all the data. Can I move offsets for consumer groups?
No, do you remember what? So now I implemented our consumer group. I'm not sure. Is he still on the line?
Yeah, I'm here.
Do you know if we ported over that topic?
You know, all the data models are basically the same. So if we can, I don't think we've tried to port data as well as the consumer group state, but in principle, yeah, in principle it should work.
Also,
I haven't done it, so I'm not sure.
outside of porting it over, external tools sometimes consume that as a way to monitor. So internally, do you recreate consumer offsets, and is it the same payloads as let's call it a normal Kafka cluster?
If it's compatible with the Kafka client protocol, then we should be compatible.
So this is a little tricky, because the contents of _ consumer offset specifically for Kafka are never a client's business, right? This is a Kafka internal state topic, although plenty of systems know what's going on there and expect it to exist. So the question is, do you guys recreate it? It is not strictly a client API.
Are you talking about the payloads inside of the consumer group?
For example, we open sourced a system called, God damn it, the name eludes me.
Burrow.
Burrow, thank you very much. And Burrow basically operates on consuming that _ consumer offsets topic, knowing what's in there and decoding that.
Yeah, so we We don't inspect internally those payloads. We have an internal topic for consumer group data, just like Kafka does. Although I think we don't use a topic, we use a raw raft group for that. Yeah, we'd have to get into like specific details. I haven't looked at this stuff in like a month, so it's fully outside of my brain at the moment. But yeah, I mean, the data is preserved the same way the clients send it. So you know, if there were some benefits to interpreting that state, we could certainly do that. But I'm not sure to what extent we do that right at the moment.
Okay, so and I was about to ask the same question for the transactional topic, but I assume.
Oh, we don't support transactions yet. That's Dennis is working on that right now. It's right now it's just the base API. So we don't have transactions yet.
So I have a question. The Kafka API supports version 2.4 supports 48 different operations.
Yeah.
And how many of those do you actually have? Do you have just produce? But what do you support and to what level?
I don't remember. No, do you? So as far as I know, basically here's the basic answer is that if they should be most of them accept transactions, and if we don't, there's a bug. If we don't, it's because
there's all kinds of extra APIs which have to do with RBAC. There's configuration management APIs. There's transactions.
Configs work, transactions don't work yet. Admin API should work. Fetch and produce should work. So okay, well actually here's the answer. We're gonna open source next Tuesday. We checked in the upstream JSON files, and we co-generate the APIs. We actually wrote a parser combinator library for C++, so we don't manually say like if version 2 blah blah blah. So you could just check whatever is co-generated there is co-generated.
Yeah, but to what version are you compatible with Kafka? Like with
I think it has to be above 2.11 the client change?
It basically, for fetch and produce, it should go back all the way to immediately after like the original record batch format was introduced, like right after that. So like, I don't know exactly what it is, but it starts like the API level is like 2 or 3 or something.
That's 0 to 10.
I don't have all the. I'm just speaking in terms of like the low level API versions. I'm not sure how that maps exactly to the Kafka versions. We generally test with like 2, 3 and later.
Thanks.
I have a quick question. I think during the talk you mentioned compaction, but I just want to double check. Is compaction fully supported?
Yeah. Well, so offset compaction is supported. I think there's like a new kip for like header-based compaction, and there's another one. So like, you know, per key with offset, that should just work. Yeah, that's fully supported.
Okay, thanks.
I'm sorry, Felix, go ahead.
No, I have nothing else. Thanks.
I'm curious about the replication protocol, specifically the segment replication. I'm curious if you guys diverged from Kafka in any way, or if it's essentially the same.
Yeah, it's pretty different in that Kafka uses like the mental model synchronous replication, and we use Raft, which can write to a quorum. And so actually Dennis just released a blog post by the way.
You actually use Raft for the segments themselves?
Yeah.
Oh, okay.
So we just released this like 2 hours ago. Actually, the difference in availability or unavailability of the different protocols, and like so definitely send us a tweet or an email if you guys want to discuss further. We'll probably also only cover about I don't know 40% of the product. So it's just like any big project, there's like way too many moving parts. So hopefully this was useful. I do have to run in 3 minutes. Any last minute questions? Nacho, do you guys have anything else that you want to add or ask?
No, I think this was great. I think maybe we can see if there's more questions. We'll capture them and